Oh, start recording. Yes. Okay, did that. Okay, excellent. So anyway, 4.8 is really just sort of like the intro to chapter 5. Some books put it in chapter 5 and other books put it in chapter 4. So what can I say? It's in 4.8 in this book, so it kind of drives me crazy, but such is life. All right, there we are recording. So I had mentioned this in the email, but basically we're going to sort of bounce around chapter 5, and this is not just specific to our class. I tend to always do the same thing every time I teach Calc 1. We are technically covering through 5.5. I don't even know if there is a 5.6. Let me check. Ugh. There might be, but I don't think we're covering it. It's not required. Yes, there is technically a 5.6, but it is not covered. It used to be covered in Calc 2, but they don't cover it in Calc 2 anymore. So I don't know. I think they just cover it in differential equations, but it's sort of like an intro to differential equations in 5.6. So we're going to cover through 5.5, but I usually go through this process where I kind of skip 5.1 and then a lot of 5.2, and to sort of give you an explanation as to why. Normally, remember how when we first started taking derivatives, we used the limiting process to do it? So you went through this whole process of taking f of x minus f of c divided by x minus c, and you took the limit as x approaches c, or we used f of x plus h minus f of x divided by h, and we took the limit as h approaches 0. And you found that to be a lot of work. And then when I taught you derivative rules, you never used the limiting process ever again. Okay, well, I taught you the limiting process for that, and some teachers skip that, but because I feel like it's a little bit more intuitive, it doesn't take quite as long, and I feel that there is some value to that. As far as covering the material in the early part of chapter 5, like 5.1, 5.2, I want to kind of give you a summary of what the sections are doing. But I found that any semesters when I've covered 5.1, 5.2, it has taken an extremely long time to get through. It's very, very rigorous, and it's just like when you take a derivative using the limiting process, you never use it again. So I want you to look through it and know that it exists, but I don't spend class time anymore covering it because personally I don't feel like it has enough value to really make up for the amount of time that it takes to get through it and the amount of effort. So I usually, and plus it's the opposite here, where in 4.8 you actually learn the integration rules, and then in chapter 5 you do all the work to get there. So it's like you already know the rules, so why are we going through all the hoopla? So that's kind of what I do in chapter 5. So I go through 4.8, and then I pick back up again at 5.3, and then we do 5.4 and 5.5. And just go through these properties. Now, the bulk of the time that we're going to be spending in chapter 5 is going to be on 5.5. I'm going to spend like 2 class days on 5.5, if that gives you any indication as to how long we're going to spend on everything else. So today's Wednesday, and then tomorrow's Thursday. Today we're going to talk about 4.8. We're going to talk a little bit about the FTC in part 1 in 5.3. And then tomorrow we're going to finish out any of that we didn't finish. And then in 5.3, we're talking about the fundamental theorem of calculus, and 5.4. And then your asynchronous work will be 5.5 over the weekend, and then we're going to do more 5.5 on Monday. Now, I emailed you a copy of our schedule for next week. So on Monday, we're going to finish out the second half of 5.5. Any questions that you had from the homework, you can ask on Monday. I might do a vote on who wants to take a quiz versus who doesn't want to take a quiz, just because, I don't know, it tends, some people are just like, let's be done with it. I don't need the pressure. I already have a test and a final, and I don't need a quiz on Monday. So we might just skip Monday's quiz, but we'll take a quiz tomorrow to go over the antiderivatives. What else did I want to say about that? Yeah, so refer to the email about this week's schedule, but I basically just gave you a rundown of what we're going to be doing in chapter 5. And then on Tuesday, if you can make the review class, that's great. If you can't, it's fine. We'll just make that our asynchronous time. So it's absolutely not a big deal whether you make it or not. Like I said, I usually only have like 2 or 3 students show up to it anyway. So I'll record it. I'll post the notes. I'll post the video. It'll probably, I'm hoping, be questions from your final exam review, which I emailed you about. It's on D2L, but I also attached it in the email. And I have the key for it. I just have to go through and reformat it. So I might just even do that by hand to save time, just so that you have it instead of you sitting around waiting for it, just because I have to get rid of some questions. Maybe I'll just do that. Anything else I need to mention? Your test for chapter 5, that will be Wednesday, and then you'll take your final exam Thursday, and that's it. You'll be done. You can go on. Enjoy the last 3 weeks of your summer before your fall semester starts. Any questions on the schedule that is forthcoming? Upcoming, I should say. Wonderful. Oh, I know you guys are tired. I know that you are tired. I'm feeling it too. I have all these tests I have to get to. I know. I always think if I'm tired, you're tired. It's kind of how I gauge it. And I'm tired right now. Hang in there, you guys. Summer classes are no joke. All right, let's talk about antiderivatives then. Okay. 4.8. And this will also just be a little bit of an intro to differential equations. So we're off to a great start. I have absolutely no lead, okay? How did this even end up back in the pencil holder? Oh. 4.8. Antiderivatives. Differential equations. So an antiderivative is probably what you're thinking it is. It is undoing a derivative. So you're going in the opposite direction. So it's almost like I gave you f prime and I'm asking you for f of x. So in order to talk about antiderivatives, we need to get a new set of notation. First, let me give you a definition. Antiderivatives. So if you're thinking about an antiderivative as something that's not a derivative, I mean, technically it's not a derivative, but it's kind of like an underderivative, like an undoing, the other direction. Okay, a function, and this is going to be sort of weird at first as we start to define this, because we're going to call it f, like capital F, because we're going to, there's a difference between capital F and little f that you will see. Is an antiderivative of little f And I guess I kind of think about f as being like the father function, like the big F, and then little f is like the baby. So like if you're thinking of the father and then what comes next from that is the baby, that's kind of the way I see it. So there's f, and then there's little f, which is your derivative. So big F is the antiderivative. So that's what you started out with. I don't know, it's a weird analogy. But anyway, and this is on your open interval from A to B if capital F prime of x is equal to little f of x for all x in the open interval. So here's the original function, little f of x, and your antiderivative is now working in the opposite direction. So it's like your original. So this is the function where you would have taken the derivative, but it came from big F. Okay, so for example, big F of x equals x squared is an antiderivative. And don't say the antiderivative, because I want to make sure that we understand this concept here, which I'm going to explain in a second. So it's an antiderivative of f of x, little f of x, which is 2x. Because capital F prime of x is the derivative, d dx, of x squared, which is equal to 2x, which is little f. So x squared is an antiderivative of 2x. However, capital F equals x squared plus 5 is also an antiderivative of f of x equals 2x. Because, and for the same reason, f prime, big F prime, is the derivative of x squared plus 5, which is 2x, which is f of x, little f. Now, maybe it was easier to see the first example versus the second, because in the second, I added a constant onto it. However, we know that when we take the derivative of a constant, that derivative is 0. So regardless of what constant I put here, it doesn't matter that it was 5. It could have been -5. It could have been 1,000. Doesn't matter. The derivative is still going to be 2x. So what this means is that capital F can be any number of different functions that are antiderivatives, as long as the only thing that's changing on capital F is that we've only added a constant. Now, if we added 5x and not just 5, well, that'd be a different case, because the derivative of 5x is not 0, it's 5. So that would change little f. However, our function can be an antiderivative and differ by any infinite number of constant values and still be an antiderivative. So I'm going to give you this theorem now that kind of covers that, and it's called the general form of an antiderivative. The general form of an antiderivative. If a function, capital F, is an antiderivative of a function, little f, on an interval I, then any other antiderivative of little f has the form capital F of x plus c. Where c is an arbitrary constant. Arbitrary means pick one. It's random. It's whichever constant you want it to be. It's arbitrary, doesn't matter. Sorry, I haven't eaten since lunch, and I have this fear now of freaking someone out by eating cottage cheese because of my 6-year-old. Also, my husband cannot watch anybody like on TV or anything eat cereal. He like freaks out about it. He has to turn away. And when he eats cereal, he puts like the box in front of him so that we can't see his face. This is what I have to deal with over here. So now I feel like I should hide myself on camera because I'm just trying to finish this cottage cheese so that I'm not starving during class. So I'm very sorry if I'm upsetting you. Maybe I should just take myself off camera for a few minutes. I feel like I need to explain that. Everyone around here is real sensitive, clearly. Okay. That's your general form of an antiderivative. So far, I've kind of said a lot, but does anyone have a question about any of this? All right. Wonderful. Okay, so let me give you some notation, and this will be for an indefinite integral. Now, hopefully later on today and definitely tomorrow, we're going to talk about a definite integral. But for now, we're going to talk about indefinite integrals. Indefinite integral. So an indefinite integral, I mean, if you're kind of comparing this to what you would do for a derivative is just some f prime of x, whereas a definite integral, which we're going to talk about later, would be when you evaluate the derivative at a number. And a definite integral would be when we're taking our antiderivative and evaluating it at endpoints. But the indefinite integral is just going to be some function of x, and it uses this integration symbol. You might have seen it before if you've taken calc before in high school or at ECC, or you might have seen it anyway somewhere in some calculus-related place. Then you wonder, what is this really cool symbol that one day I'll get to use? Well, it's an integral symbol. It sort of looks like an elongated S. That's actually the origin of the symbol. It was supposed to represent a summation, which we'll talk about more in chapter 5. But it's this elongated S, and you do your best to just make it look nice. My teacher once told me you make a hook that goes halfway down this way and then go another halfway down and make a hook in the other direction. That's all it is. Yeah. I mean, don't make it look too S-ish, otherwise it'll look like a 5, and you don't want to have 5s randomly in your work. It'll throw you off. So do try to make it elongated at least so you can tell the difference. Okay, so we have the integral of f of x dx. F of x is your integrand. Whatever function is in there, you're not usually going to see f of x in there. It'll be some function of x. Dx is part of the notation that represents your variable of integration. And pretty much in Calc 1, that's just going to be a formality for you, but you do have to include it. Later on when you're in Calc 3 and you're taking double integrals or triple integrals and you're working with all different kinds of variables, it's going to make a big difference to you what that variable of integration is. Even in Calc 2, especially the first chapter we're going to hit in chapter 2, in Calc 2 if you're in my class, it's going to be really important that you note your variable of integration as you work your way through. So this, like I said, it's part of your notation. It has to be there, but that's what it represents. And then this is equal to your capital F of x plus c. So remember, we defined capital F of x as your antiderivative. And then c is going to be your constant of integration. If you want to call it your arbitrary constant of integration, that's fine too. Arbitrary constant of integration. It is going to have to be included on your answers. And if you're wondering, like, okay, she's probably going to switch this to a number. No, I'm not. C is going to always just be C. It's not going to switch to some number, because remember, C can be any number. We talked about the fact that your antiderivative is only different because of this constant that's tacked onto the end of it. So your dx will always be dx as long as you're taking an integral with respect to x. And c will just be c. Whatever your antiderivative is, that's just going to be some function of x. And this means that capital F prime of x is equal to little f, just like we defined it. If you're looking for a little bit more notation, if you find that this is just really random and you want to sort of get a better sense of where it comes from, well, remember that when we talked about derivatives, I gave you this Leibniz notation for dy dx. Well, remember that your derivative is your little function f in this case. So we would say that dy dx is equal to f of x. And then when you multiply both sides by dx, you end up with dy equals f of x dx. And hopefully now you're starting to see where this integral notation comes from. We'll go through this process, and even today, where we take the integral on both sides. I've been saying derivative for the past 6 weeks, so I'm going to have to remind myself to say integral. So if you catch me saying anything that's out of place, please let me know, but I should be good. It was very confusing last semester when I taught Calc 1 and Calc 2 at the same time, just trying to keep straight where everybody was, because you rarely talk about derivatives in Calc 2. So the integral of dy is then y, and we know that y is equal to the integral of f of x dx. So this is the antiderivative of the derivative. So it's kind of like an undo. You take a derivative, but then you take its antiderivative and you're right back where you started. It's kind of like when you use an inverse process. That's what that looks like. Yes, Renee, go ahead.
Wait, so can you repeat that again? You said that the integral of dy equals y is the integral of f of x times dx?
Yes, this part right here.
Okay.
Yeah, this is what you're asking me about, right?
Mm-hmm.
Okay, yeah, so so you can start out by, we said our derivative was little f, and then multiply both sides by dx, and then you get dy equals f of x dx. And then if you want to just get back to y, you can take the integral of both sides, and we're going to do this today when we work on just some very elementary differential equations. And then we can say that the integral of dy is y. You'll see this when we go over the rules actually in a little bit, but it also is just sort of like if dy is a derivative, you're taking the antiderivative of a derivative and you're just getting the original back. So it's like taking the derivative takes you down a notch, and then taking its antiderivative brings you back up to where you started. So it's kind of like it undoes it. So if you have y, you take its derivative, and then you take its antiderivative, you're right back at y again. I know it's kind of a weird concept, but does that help?
Yeah, it does. Thank you.
I always also tend to think of derivatives and antiderivatives as going down and up. I don't know why. For me, that's just the visual that I come up with, because I guess I always take a derivative heading downwards, and then if I think of an antiderivative, it's like I'm going in the reverse direction of where I started. So it's like I'm going up. And if I take a derivative, I'm going down. So if I'm doing a lot of this, I guess that's just the way that I think about these things. But if you'd like, you can think about this also in reverse. If the integral, sorry, I forgot my integration symbol, of f of x dx equals the antiderivative, capital F plus c, then we can also say, and I'm just playing around with the notation here, it's certainly nothing super crucial, I just think it might be helpful to understand how the notation works. The derivative of the antiderivative, and this is sort of using that same idea, is like you're undoing it. So you took the antiderivative, but then you took the derivative, so you're right back where you started, and you get the integrand to pop out. So the integrand is really just the derivative of the antiderivative. It gets you back to where you started. So that's kind of the same way of saying the same, or a different way of saying the same thing, I should say. Was there one more thing I was going to say about this? I had one more note on here. I don't know if it's going to be helpful or more confusing. The integral of f prime dx equals big F plus c. So it's, again, this process of you're undoing, you're taking the derivative and you're taking the integral. It's like they cancel each other out, and what you're left with is just whatever the original was. Same idea. Okay. That's all I have to say about notation, though. I want to go over some rules now. Okay. So I'm going to go straight to the power rule for integrals, because you're going to use it all the time. So I'm going to give you a series of rules like I did for derivatives, but this will be for antiderivatives. So if you'll remember back in, I want to say 2.3, yes, 2.3, we learned a bunch of derivative rules. Now we're going to learn how to undo those rules and get the reverse. Basically, that's what we're going to be doing. The integral of x to the nth power dx. So if I give you an integral and it's of the form x to the n, where n is going to be some integer, or technically n can be any rational number according to the rules that we went through in the last section. But really it can be any real number. Your book just never defined it that way. Instead of bringing the exponent out front and subtracting 1 from your exponent, you're going to put that 1 back in the exponent, and you're going to divide by the new exponent. So you're going to take your value of x, your variable, you're going to increase the exponent by 1 instead of decreasing it by 1, because we're going in reverse. And instead of multiplying by the exponent, you're dividing by your new exponent plus c. And this will be for any value of n not equal to -1. We'll have a special case when n is equal to -1. And if you're wondering, like, why does it matter if n equals -1? Well, think about what your integrand would be in that case. If you had x to the negative first, that's 1 over x. 1 over x is a special derivative. 1 over x is the derivative of the natural log of x. So we're going to talk about that as we work through here and get these rules together. But yeah, basically this rule applies as long as you don't have n being -1. And think about if you tried, if you didn't remember that rule didn't apply when n equals -1. If you took x to the -1 plus 1, you'd have x to the 0. And then if you divided by -1 plus 1, you'd have a real problem on your hands. So that's not going to work for you. Now, your book doesn't give a special case for this. I don't know why. So I'm going to make sure I put a note in here for it. The integral of k dx, where k is a constant function, so it might be like the integral of 3 dx or negative 5 dx, something like this, is kx plus c. And the nice thing about integration versus differentiation is that you can always work your way back the other direction because you know how to take the derivative. So the value that you have on the right should have a derivative that matches the integrand that you see on the left. So the derivative of kx, where k is a constant, would be k. So you can sort of see how this works in reverse. So if you're taking the integral of k dx, well, that ends up giving you this quantity kx, and we always have to add the plus c on there. Now I'm going to give you some examples of how to use these. So if you're like, well, this is weird, I don't know what's going on, don't worry. I've got you. I've got many examples. I always have a plethora of examples to share with you. All right. Example 1. Evaluate. I'm going to give you some integrals here to work with. The first one is the integral of x to the 4th dx. And by the way, when you start Calc 2, which for some of you will be a little bit less than a month from now, you're going to be expected to know how to integrate very well from the beginning. And a lot of the functions will be more simple, but some of them will have more complicated integrals to them. And then you'll learn a whole bunch of more techniques for integrating in Calc 2. Okay. So we're going to do here, I'm going to keep my rule here. In this case, I have x to the nth power. I don't have anything else in this integrand. I just have an x to some sort of constant power. So I'm going to leave the x right where it is. Now, once you evaluate the integral, drop the integration symbol. So it should not be on your final answer. It's kind of like how when you apply the limit, you drop the limit. Same idea here. You're going to increase the power by 1 and divide by your new exponent. And don't forget your arbitrary constant and simplify. Now, in a lot of cases, because you're going to be doing it in exactly this manner, you might just leave it as x to the 5th over 5 plus c. If you want to leave it like that, that is totally fine. If you don't like x to the 5th over 5, you can write it as 1/5 x to the 5th plus c. These are equivalent. They are both simplified, and they're both wonderful answers. Sometimes I find that students like the second answer better just because they like to think about it as multiplying by 1/5 instead of dividing by 5. I don't know why, but it does not matter. Maybe it even just depends on what application you're working with. The nice thing is that, like I said, with the derivative, you can go backwards to check. So you can take your non-plus c portion of the answer here that you obtained and take its derivative. So 5 times 1/5 is 1. Decrease the exponent by 1 and you get to 4. And it gets you right back to your integrand. So I just want to make a note of that. The derivative with respect to x of 1/5 x to the 5th, plus c, I should say, because technically it is part of our answer, is just going to be 1/5 times 5 times x to the 5 minus 1. And remember, the derivative of any constant is 0. So this gets you right back to x to the 4th. If you want to check these, you can. Some of them will be easier to check than others. Sometimes it helps just to do a quick mental check, not really writing it down. Certainly nothing that you have to show to me that you checked. Just gives you sometimes some peace of mind knowing like, okay, this makes sense, especially when you're first starting out on these. Any questions on A? And I hope that some of you are starting to kind of take a deep breath and feel a little bit more relaxed, because really Chapter 5 is going to be a little bit of a breather for you. Even though technically integration can be very hard, what we're doing in this class is not going to be too crazy. Every once in a while, you'll see something that gets a little wacky, but it's not going to be like, oh my gosh, I'm dying in this chapter. Usually students do pretty well on their Chapter 5 test. And remember, I dropped your lowest test, so if you're thinking that it was the last one, it's okay. Like, move away from it. I don't know how bad they are. I just know that I usually flip through the test real quick just to make sure that nobody submitted a blank exam. I have had that happen a lot where students will just upload like the blank test I sent them. I don't know how that happens, but I always leaf through them just to make sure it's your actual test. And it seemed like there were lots of blank portions on the exams. That's all I'm going to say about it. I have not actually given them a thorough evaluation at this point. The test score is usually overall not as good. That's why I'm assuming that it's not as good here, but maybe I'm wrong. Maybe you guys did an awesome job. And for some of you, it will be your best test. It will be. But for probably many of you, it'll be one of your lower ones. Okay, so for B, we have the integral of 1 over the cubed root of x dx. Now, just like with derivatives, we're going to have to rewrite these integrands to fit the rules that we have. And you're going to find with integration that you actually have to have a lot more rules involved, because you're going to have a hard time fitting some of these forms. All I've given you right now is a power rule. So that's all you have to work with. So in order to match your power rule, you need to have an x not in the denominator. And I want to make that very clear. You cannot take the integral of the numerator and divide it by the integral of the denominator. And we made a big deal about that with derivatives, because remember, for derivatives, I gave you a product rule and I gave you a quotient rule. We don't even have product and quotient rules for integrals. We're going to have to just do substitutions in 5.5 to undo those products and quotients. So no matter what, just remember, you cannot take the integral of the numerator and denominator separately. It does not work that way. We must rewrite this to match some sort of rule. Remember that a cube root is a 1/3 power. When I bring this 1/3 power, and if you'd like, I'll do this in 2 steps. We can write this as 1 over x to the 1/3 dx. And then we can rewrite that as x to the negative 1/3 dx. All right, now it matches the form for your power rule for integrals. In order to integrate, I'm going to leave the base alone. I'm going to increase the exponent by 1, and you're going to get good at this, and you're not going to keep writing like the exponent plus 1 divided by the exponent plus 1 and simplifying. You're going to do it all in one fell swoop. But for right now, this is all new, so I want to make sure that it's very clear as we go through here. So I'm going to show my simplification. And just like with derivatives, we're going to get really good at adding and subtracting 1 from these fractions, or I guess technically in our case, adding 1. So negative 1/3 plus 1 is positive 2/3. And then we're dividing by positive 2/3. That is technically a complex fraction. Please simplify that. Instead of dividing by 2/3, multiply by the reciprocal. We can rewrite this as 3/2 x to the 2/3 plus c. And remember, you can always go back and check this if you would like. 3/2 times 2/3 does indeed give you 1 as your constant multiple, and then subtract 1 from the exponent, you get back to x to the negative 1/3. Questions on B? Wonderful. Okay. I'm going to give you C now, which I never used to include. But I had a student one year in Calc 2 from day 1 fought me on this. Like, could not wrap his head around this in Calc 2. And I thought, you know, if we're going to have this much trouble over something so basic, things will not go well here. And they did not. So I want to make sure we understand this. The integral of dx is equal to the integral of 1 dx. It's like when you have just x. You don't write 1x usually. I mean, you can, but you don't have to. The 1 is assumed. It's not equal to the integral of 0 dx. If we had the integral of 0 dx, then we would have nothing. We wouldn't have this. So I want to make sure that we understand the difference. Okay, so the integral of dx, and you're not going to see it a lot, but you'll see it from time to time. This is going to use that rule for your constant function. I'm going to remind you, I gave you this note up here. In our case, the constant function would be 1. So we're going to take that 1 and we're going to tag an x onto it and add c. So there's your k. So the integral of dx is going to be equal to, and like I said, we're going to just take our 1. I feel like I need to write this one more time. We're going to take the 1 times x plus c. Just really want that to be clear, because this is just one of those very subtle things that drive students crazy because it's so subtle. So anytime you're just integrating a constant, you just multiply it by x, add c, and you're done. And remember that you can go through and check. The derivative of x is 1. 1 is indeed the value that's in the integrand. Okay. Questions on C? Is that going to bother anybody? Okay, good. I'm going to give you a rule now for integrating the sum and difference of two functions. I know that we just assume we can do it, but I want to make sure that we understand that we officially have a rule for it. So this is the sum and difference rule. If capital F sub 1 and capital F sub 2 are antiderivatives of little f sub 1 and little f sub 2, respectively, then big F sub 1 plus big F sub 2 is an antiderivative of the function little f sub 1 plus little f sub 2. And we can do the same thing for the difference. Big F sub 1 minus big F sub 2 is an antiderivative of little f sub 1 minus little f sub 2. So there's your sum and difference rule. All right, now we're going to combine that with the constant multiple rule. I'm going to give you some examples that use both of these rules at the same time. You've seen sum and difference rules a couple times now. You've seen them for limits, you've seen them for derivatives, now you've seen them for integrals. Same with constant multiple rules. In all three cases, you're seeing the same type of behavior. If k is a real number, and f is an antiderivative of little f, then kf, or I should say k big F, is an antiderivative of k little f. So this means that if there's a constant multiple on our function, if we would like, we can pull it out of the integral, or we can leave it in. Doesn't matter. No matter what, if our integral is getting multiplied by a constant multiple, then our value for the antiderivative is also getting multiplied by that constant multiple. It's just kind of getting tagged along. Example 2, find all antiderivatives. I'm giving you these directions using different wording each time, but basically what I'm asking you to do is evaluate the integral. Find all antiderivatives. And if you're wondering, like, wow, that sounds like a really different instruction than she gave us last time. Is there more work we have to do here? No. When I say find all antiderivatives, that basically just means, like, make sure that each one of your answers has a plus c on it. That's basically all I'm saying. All right, so A is going to be the integral of 3x minus 1 dx. Now, normally when you put more than one term in your integrand, we use parentheses around the terms just because you want to make sure it's very clear that that entire piece is inside your integrand. I can't force you to do it, but it looks better. And you'll see that that will happen on WebAssign, and I'll always put the parentheses around it. You want to make sure it's clear where your integrand starts and stops. Okay, now you're going to get used to doing this without splitting it up. But basically what this means using your sum and difference rule is that you can take the integral of 3x dx and subtract off the integral of 1 dx. There might be instances where you want to write these integrals separately, and you'll see some of these instances next week on Monday and maybe over the weekend, possibly. You might find it easier in some cases to split them up just because you might have two very different functions in each term. In a case like this, you probably won't split them up. I just want you to know that you can. So the integral of 3 dx we can also write as 3 times the integral of x dx, and then we still have minus 1 times the integral, or I'm sorry, minus the integral of 1 dx. So here in this first expression where I split these two up is where we applied the sum and difference rule. And now in the second rewrite, when you see that the 3 is getting multiplied by the integral, that's where we're using the constant multiple rule, just pulling that 3 out of the integral and putting it in front of the function. You don't have to put it in front of the integral, does not matter. As long as it's still there, that's all that matters to us. I personally like looking at it this way better most of the time. You'll find that sometimes it's helpful to leave it in, otherwise you might forget that it's out there. So there's that. Okay, so I'm going to take 3 and I'm going to multiply it by the integral of x dx. I'm going to take our x, I'm going to increase the exponent by 1 and divide by the new exponent. So the current exponent is 1, not 0. Just because you don't see it doesn't mean it doesn't exist. X is just x to the first. So we have that, and then we'll subtract off the integral of 1 dx, which we just went through in the last example, and we said that that was x. And then you can just pop a plus c onto the end. So you don't have to put it on every single time. And sometimes your book gets really pedantic about adding a c here, and then adding a c sub 1 there, and then in the answer they write it as c sub 2. I don't care. They're all constants. Doesn't matter to me. Okay, so we'll have, in the denominator, 1 plus 1 gives you 2. So I'm going to write this as 3 halves, and then x to the 1 plus 1 is x squared minus x plus c. Okay, any questions on that example? Oh, so Renee's asking, will there ever be a case where C is negative? C can always be negative. It represents any sort of constant. So whether you're adding or subtracting the constant, if you took its derivative, you're going to get 0 regardless of whether it's positive or negative. So we always write plus C, but you could technically write minus C, and I'd be okay with that. I'm assuming WebAssign would accept it. I don't see why not. So, I mean, you could technically write like minus 5C, and it would technically be right. It would just be kind of silly. But yeah, you could write minus C or you could write plus C, but C could represent a negative value. Yeah, so good question. I'm glad you asked. So yeah, technically fine. This is just the standard convention for writing it. Other questions on example A? Okay. B. This is the integral of 2x cubed plus 2x squared minus x plus 1 dx. Now, it's up to you if you want to pull out these constant multiples. It's up to you if you want to split up the terms. I'm not going to keep doing it because I don't think you're going to keep doing it. When you're going through your homework, my guess is that you're going to say, okay, I'm going to bring down the 2. I have x to the 3 plus 1 divided by 3 plus 1. And you might not even do that. You might automatically go to x to the 4th. I think that's what you're going to do. So you're going to take your exponent, you're going to add 1 to it, and you're going to divide by the new exponent. That's the process that I think you're going to apply here. Then you're going to rewrite this 2. You're going to increase the exponent by 1 and divide by the new exponent. Same idea. Increase the exponent by 1, divide by the new exponent. And then for a constant, you just multiply it by x. Don't forget your plus c. And then we'll simplify, although there's not a whole ton to do here. Before I simplify, are there any questions on the antiderivative?
How did x become positive again?
X. This one?
Yes.
Well, I had a positive 1, so I just took the positive 1 and multiplied it by x.
Oh, okay.
Did I answer your question? Because I saw the, you know what's amazing, Burfin, is because you keep your camera on, I saw you as I was going through this, and I was like, I bet you she's going to ask a question. She's got that questioning look on her face. So I want to make sure that whatever the question was, I addressed it.
Yeah, thank you.
Wonderful. All right, so to simplify, I'm just going to simplify between the 2 and the 4 just by removing a common factor of 2. And then I like to write my constant multiples as fractions in front instead of just showing this as x to the 4th divided by 2, but it doesn't matter. So this would be my rewrite. And in some ways, you might glance at it quickly and think that it's a different function, but it's really not. So really, the only thing wrong with the original was just this 2 over 4 wasn't simplified. That's it, though. Everything else in it was fine. Okay, so example C, I really like. This one is the integral of, and I'm going to give you a quotient here. The numerator is x squared plus 1. The denominator is the square root of x. dx. Now, we did examples similar to this when we were taking derivatives, and we talked about how you can't just take the numerator and denominator and split it up and take the derivative separately. Same idea here. You're going to have to rewrite the function. Must rewrite. We don't even have a quotient rule for integration. The only way you're ever going to be able to do a problem like this is to rewrite the function. It's kind of a scary thought, isn't it? No quotient rule for integrals. All right, so we're going to rewrite the function. I'm going to take it out of the integrand for a minute just so I don't have to keep rewriting it. And I'm going to rewrite the denominator, the square root of x, as x to the 1/2 power. And similar to what I did for derivatives, I just want to split this up into separate terms so that I can simplify the variable expression on each term. So to do that, I'm just going to use the common denominator and split it up. And some of you are pretty good about doing this without showing a whole lot of work. Others like to see the algebra. So this is just x to the 2 minus 1/2 plus x to the negative 1/2. Remember, if you're dividing and you have the same base, you subtract the exponents. So 2 is 4/2. 2 minus 1/2 is x to the 1.5, or x to the 3/2. And I can leave the second term alone. I do want the exponent to be negative because I don't want the variable in the denominator. The variable cannot be in the denominator. But now that you've rewritten the expression, you can go ahead and put it back into the integral. So this is the integral of x to the 3/2 plus x to the negative 1/2 dx. And now you can use your rules for integration. The only rule you're going to need is the power rule to take the antiderivative. So I'm going to have x to the 3/2 plus 1 divided by 3/2 plus 1 plus x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus c. And again, I'm showing more work than I expect that you're going to show here. Just because it's new. I'm assuming it's new to most of us. So 3/2 plus 2/2 is 5/2. So I have x to the 5/2 divided by 5/2. Negative 1/2 plus 1/2, or I'm sorry, negative 1/2 plus 1 is 1/2. And then instead of dividing by a fraction, this is technically not simplified. I'm going to multiply by the reciprocal. So instead of dividing by 5/2, I'm going to multiply by 2/5. And you can leave your answer like this using rational exponents. That's completely fine. But this does remind me, last week we were talking about rewriting stuff like this. I think it was because you had to evaluate it, and you will eventually at some point have to evaluate things that are in this form. And if you're not sure how to write it in a manner in which you can easily evaluate it, remember, side note, x to the 5/2 is really just x to the 2.5. And if you are multiplying and you have the same base, you add the exponents. So you could rewrite this in the opposite direction as x squared times x to the 1/2. So this would be x squared times the square root of x. In case you had to evaluate this, we will get to a point where we would have to evaluate this. So if you were rewriting this with radicals, and sometimes it's nice to leave our answer in the form in which we received it, which was with radicals, you could rewrite this as 2/5 times x squared square root of x plus twice the square root of x plus c. And that would be an equivalent way of saying the same thing using simplified radicals. Just an algebra side note, because I think it's good to keep going through those and, just, the consistency, seeing it often, working our way back and forth between the two forms. And because I enjoy doing it. Okay. Questions on C? Because I have another rewrite coming up after this. D. This is the integral of x squared minus 1 quantity squared dx. Okay, if it looks like something that you would have to technically unchain, then you're going to have to rewrite it. And this looks like something you'd have to unchain. You cannot write this as x squared minus 1 quantity cubed over 3 plus c. That's a big no. Don't do it. Cross it out. You can't just take the variable expression, increase the power by 1, and divide by the new exponent. That only works if the base is x, just x, not x squared minus 1. This is a function of x. It doesn't work that way. If it requires the chain rule to take a derivative, then you cannot just use the power rule on it. So what you're going to have to do is rewrite this, but no big deal. You know how to multiply a binomial by itself. You just write it as x squared minus 1 times x squared minus 1. And this is also where I would tell my algebra students that this does not equal x to the 4th minus 1. Very, very common algebra mistake. Make sure that when you're squaring a binomial, you're actually multiplying it by itself. So you'll have x to the 4th minus 2x squared plus 1. Now you can put that back into your integral. Don't forget your dx's. But now this looks like example B, which was just a polynomial function with several terms in it. But sometimes you'll just have to rewrite it to get it there. Increase your exponent by 1, divide by the new exponent. Do it again. And the antiderivative of 1 is 1x. And I mean, technically this, I guess, is fine. I would accept it, I guess, but it would look nicer if you wrote this as 2/3 instead of twice x cubed over 3. Okay, so there's a table in your book on page 344. And if you don't have the book, no big deal, because I'm going to summarize this whole table for you. It's going to take a minute. But it's going to have a bunch of different antiderivatives on it. Page 344 is where you would find it, and it's table 6. But I'm going to list them out for you because they're common ones that you're going to need often. One of them is that case, remember when I gave you the power rule and we said that doesn't work if n is equal to -1 because your function would be 1 over x. That's in the table also. So I'm going to give that to you now. So let's say f of x, little f, is x to the negative first, that special case where n equals -1, where we can't use the power rule. Our original function in that case, however, knowing what we know about derivatives, we can work our way backwards. Our original function would be the natural log of x. However, when we create a natural log, we need to make sure that we put absolute value bars around the variable expression inside your log. Remember, that's because we can only take the natural log of a positive number. Only positive numbers are included in its domain. So when we create that natural log out of nowhere, we need to force this value of x to be positive. It might not have been, I mean, because over here, you have no indication that x has to be positive. X can be any number. Make sure that you indicate that by including those absolute value bars on your natural log expression. So that's the first one in the table. Very important that we will use. Another one you're going to see a lot is e to the x, but you know that the derivative of e to the x is e to the x. Therefore, the antiderivative is e to the x plus c. One that you're not going to see as often, but we definitely talked about it as it related to derivatives, was when you had a base other than e. So a to the x. Your antiderivative is a to the x divided by the natural log of a plus c. And this applies to a being positive and a being not equal to 1. So you'll see it here and there. You won't see it a lot. You'll see it just often enough where you're like, ugh, dang, I have to go back and look and figure out what that integral formula was because I don't remember. By the way, I keep using this word integral. We talked about a notation using an integral. When you're taking an antiderivative, you are integrating. We'll use that term a lot more in chapter 5. In chapter 4, you tend to see it written as antiderivative because technically integrals haven't really been defined in chapter 4. All right, so we have the basic trig functions. Now, working your way backwards with these is a little bit trickier because you have to remember which one has which sign. So remember that the derivative of sine was cosine, but the derivative of cosine was negative sine. Remember that the function on the left is the derivative. So in order for your derivative to be positive sine, your original function had to be negative cosine. Honestly, I don't ever remember that formula. I just always go back and forth in my head as to like, okay, if the derivative of cosine is negative sine, the derivative of negative cosine is positive sine. That's just what I do. You're going to find that in Calc 2, if you miss the sign on these, S-I-G-N, your whole answer is going to be wrong just because it's all going to be based off the wrong sign, S-I-G-N. So that's a very, very common error. Just watch out for that. If your derivative was cosine of x, well, that came from the original function being sine of x. So remember, big F is your original, little f is its derivative. Okay, so one of the trickier things with integration or antiderivatives is that everything kind of has to fit the form that you saw it in for a derivative. So I'm not going to give you, for instance, f of x equals tangent x because you don't know of any function whose derivative is tangent x. But I can give you f of x equals secant squared x because you know that the derivative of tangent x is secant squared x. You see how that works? So it's a little trickier. And if you're wondering how many more of these I have, it is 6 more. All right, we also have, in a similar vein, cosecant squared x. The derivative of cotangent is negative cosecant squared. So our original function must be negative cotangent x plus c. And if you're thinking about this where the cos must be negative, that still applies. The cosine, the cotangent, still negative. And then you had a derivative that was secant x tangent x. And that original function was the secant x, secant of x plus c. Same idea for cosecant x, cotangent x, but the cos are always negative. So your original function was negative cosecant x plus c. Now the last 3 I have for you are for inverse trig functions, and we're going to do a lot of work with these probably on Monday. We're going to really focus on these, maybe a little bit for the asynchronous work. So I'm going to give you the form here for these special inverse trig functions where you're seeing just the derivative. Don't pay too much attention here. You're not going to see anything that's not going to be workable for you. It's more of a formality. The derivative of the inverse sine of x plus c is 1 over the square root of 1 minus x squared. But you'll find that you'll have a surprising number of integrals that follow this form, so that you're going to have to work your way backwards to an inverse trig function. Okay, I'm going to give you the other 2, and then I want to make a special note about the cofunctions. So one you saw quite a bit of was 1 over 1 plus x squared. The original function was the inverse tangent of x plus c. And then the last one is 1 over x times the square root of x squared minus 1. We didn't use this one quite as often, but it was for the inverse secant of x. Oh, and this assumes that your x is greater than 1 just by the rules for that function. Okay, now I always have at least one student who's thinking this. You didn't give us rules for the inverse cosine, you didn't give us a rule for the inverse cotangent, and you didn't give us a rule for the inverse cosecant. That's because, if you'll remember, the only difference between these 3 forms on the left was that for inverse cosine, cotangent, and cosecant, you had a negative in the numerator. That's the only difference. So we don't need to worry about that in this case. When we're going backwards, we'll just generalize that to be of these functions over here on the right. So if you did have it as a -1 in the numerator, you could technically say it's an inverse cosine, or you could just say it's the negative inverse sine of x plus c, because it would be a constant multiple in that case. So it's a little bit easier when you're working with this particular form as far as integration is concerned. Okay, now let's work a little bit with these new forms, and then we'll talk about some differential equations. Example 3, integrate. That means find the antiderivative. A, this is the integral of -3 cosine x dx. I find that with these trig functions, like I said, students tend to mess up these signs. So if you would like to move that -3 in front of the integral symbol, just so you can focus on the cosine of x, you might want to do that in this case. This would definitely be a case where I would find that to be helpful. Because sometimes you end up with a bunch of different negative signs and then you lose track of what's going on. All right, so you're asking yourself for these trig functions, at least this is what I do in my mind. I go in reverse. I ask myself, what function has a derivative that's cosine? Well, I know that the derivative of sine of x is cosine of x. So it must be the case that my antiderivative is -3 times the sine of x. So the -3 just came down. The derivative of sine is cosine, so the integral of cosine is positive sine. Done. Now, you're not going to see a whole lot of emphasis on trig functions in Calc 1. You're going to see a whole section or two of it in Calc 2, where you're specifically focusing on how to take the integral of trig functions, depending on what's in your integrand. Here, you're just going to be doing some rewrites. Nothing too crazy. So again, you're going to have to rewrite this function because you definitely cannot integrate it in this form. You need to simplify it down. So if you would like to take it out of the integrand for a minute, you can. And then we'll put it back in once we've simplified it down a little bit.
Bless you.
Thank you. I'm going to rewrite the tangent. Thank you. As the sine of x over the cosine of x. So that's my tangent. And then I still have in the denominator, and it kind of depends. When I rewrite this, I'm just going to leave these in a separate factor. It's up to you what you want to do. I still have a sine and a cosine in the denominator. And then you can cancel out a factor of sine x. And you get 1 over cosine squared x. And if you're thinking like, okay, fine, this doesn't look that great, actually it does, because remember, you're trying to match this up with a derivative that you know something about. If I wanted to make this cosine squared x a secant squared x, I could by moving that cosine squared up into the numerator as secant. So remember that secant is 1 over cosine. We're going to use that. And then if you're still thinking like, this is no good, it is good because the derivative of tangent is secant squared. So for these trig problems, you're always thinking about them in terms of their of matching it up with a derivative you already know something about. So we know of a derivative that's secant squared, and that would be for the tangent of x. So put your integral back together, rewrite it as secant squared x. Don't forget your dx. Your Calculus 2 teacher is going to get very upset if you're writing a bunch of integrals without dx's on them. And I might be more lenient than others. The derivative of the tangent of x plus c is the secant squared of x. Done. All right, so one you're going to see quite a bit is this situation where you have x in the denominator and a constant in the numerator. And sometimes the constant multiple is distracting. If it's distracting you so that it makes it hard to see your integrand as a derivative, take it out. Rewrite it like that, 3 times the integral of 1 over x dx. And if you write it like that, then you'll notice, like, wait a second, my integrand is a special derivative that I know something about. The derivative of the natural log of x is 1 over x. So you're going to rewrite this as 3 times the natural log, and don't forget your absolute value bars. That's part of your solution here, plus c. I think WebAssign is picky about those absolute value bars, and I am too. On a test, if you forget them, you'll lose a point. And some of you are very, let's just say, upset about 1 point versus another. So I don't want you to feel like you lost a stupid point. That's what students always say. I lost all these stupid points. I mean, it seems stupid to you, but it's really not stupid at all. I get that it's like a silly mistake, but remember your absolute value bars. Students are always telling me, oh, I made a lot of stupid mistakes. I hear it a lot. Such is life. Questions so far? Doing okay? All right, I'm going to give you a quotient here. X to the 5th minus 4x squared plus 5 divided by x cubed dx. And this is another one that we're going to have to rewrite. If you want to take it out of the integral and rewrite it, fine. If you want to leave it inside, fine. But you're going to have to split up that quotient because we don't have a rule for this. So you're going to have x to the 5th over x cubed minus 4 times x squared over x cubed plus 5 over x cubed dx. And then we'll simplify again. So we'll have x squared minus 4 over x. And now when you rewrite the 5 over x cubed, you're going to have to write the x cubed as x to the negative 3rd power because we can't leave x in the denominator if the exponent on it is anything other than just 1. So this is very similar to, I believe it was example C that I did in example 2. This time we're bringing in this new form for your logarithm. So you'll have 1/3 x cubed minus 4 times the natural log of the absolute value of x. And then if you want to write the last term in 2 steps, that's fine. You'll have x to the, be careful, negative 2nd. When you add 1 to the exponent, if the exponent's negative, it's going in reverse. So negative 3 plus 1 is negative 2. Divide by the new exponent plus c. And I mean, technically, I would accept this. I think it could look better. Hence, I'm going to rewrite mine. 1/3 x cubed minus 4 ln natural log x minus 5 over, I'm even going to write the x squared in the denominator. 5 over 2x squared. And actually, the more I look at this, I don't know if I would accept it because this whole plus a negative thing would probably, I mean, if I would be consistent about it, if I took it off for one person, I'd take it off for everybody. So just don't do plus a negative. Switch that over to a minus at least. Questions on D? For e, we have the integral of 7 e to the x dx. And again, if the 7 is throwing you off, just pull it outside of your integral. It's a constant multiple, you can do that. The derivative of e to the x is e to the x. The integral of e to the x dx is e to the x. So we have 7 e to the x plus c. Don't make it harder than it has to be. I want to talk about some differential equations now. You will like these. Of course you will. There's nothing to not like about them. They're kind of fun. I'm going to show you how these work in an example, and we'll talk about them. Basically, the idea behind these differential equations is you're going to zero in on a unique solution. So instead of saying, well, our answer has to be, you know, this function plus c, that means it could represent any family of functions. Remember that when you add a constant to a function, you're just vertically shifting it up or down. What you're going to be given here is an actual function value so that you can narrow in on the value of c. So you're going to get an actual function answer here that's not written in terms of c. So example 4 is going to be find the particular solution for each differential equation. And as we go through the solution here, I really want to talk about what it means. I think it's pretty straightforward. I'm going to give you this in 2 different notations because I've had students be confused about one or the other, and your book gives you 2 different ones. So I want you to see both. dy dx is 2 over x cubed when x equals 1, y equals 3. But this is basically just telling you that this is a point on the graph of the original function. There's a point on your graph when x equals 1 and y equals 3. That's where you're going to be able to find that particular solution. If you want, we'll kind of graph it, and then you can see why it's a particular solution to this differential equation. All right, so here's what we're going to do. You're going to rewrite this as an integral. And most of the time, you don't need to, you don't ever actually have to show me like you're cross multiplying, but I want you to see why this is working. So I'm going to show it to you in this way. We're going to multiply both sides, kind of like how I did in the beginning, by dx. Because I want to turn this into an integral. So dy dx is my derivative. I'm going to take its antiderivative, and I'm going to do that here by taking the integral on both sides. And the integral of dy, and now you can see why this works the way it does. If your integrand is 1 and you're integrating with respect to y instead of x, then you're going to end up getting a y here equals the integral of twice x to the -3rd power dx. So this just uses that constant rule for integration that I gave you previously. And I also gave this to you in the notation before I gave you the rule. But if you feel comfortable with this as you're working through your homework, or if I give you something like this on a test, you can go straight from the problem statement, dy dx is 2 over x cubed, to this equation. That's fine. You can go right from here to there. I'm good with that. You don't have to show me the 2 intermediate steps. So now we'll go ahead and integrate. And I'll say that y is equal to, and if you want to put the 2 out front, you can. You don't have to. It's a constant multiple. It's going to stay there. Increase the exponent by 1. Divide by the new exponent. Add c. And when you simplify this, you'll get 2 divided by -2, which is -1. I think it's easier, since we're going to have to solve an equation, to write our exponent as a positive exponent and float that into the denominator. I would do that in these particular instances if I were you, because we're going to have to solve for c. So I want to show you something first. You end up getting here this family of solutions. And what we're going to do is we're going to narrow in on the one that's the right solution for us. If you were to graph -1 divided by x squared, you would get a graph that looks like this. And this would just be the case that c equals 0. So I guess I'm not going to write this down because it's not really part of the lesson. I want you to understand the point. So this would be the case of c equals 0. I'd have -1 over x squared. What we're looking for is a function that looks like this, but we're trying to find a c value such that when x equals 1, y equals 3. Well, you can see here in this case that when x equals 1, it looks like y equals -1. You can verify that from the table. Oh, it's right there, actually. If x equals 1, y equals -1. So this is certainly not our function. And you don't have to sit here and do a guess and check. I really just want you to see what this family of functions looks like. If you were to actually go through here and use different values of c, you would see this family of functions pop up. So like, let's say we let c be 1, or c could be something like -2. So Renee was asking, can c ever be negative? Sure. You could even let c be something like, I don't know, 6. +6 or -6, doesn't matter. But what you're going to see here is this family of functions that all has this same antiderivative, but they're all going to be separated by these constants, which represent these vertical shifts up and down on your graph. So remember, anytime you add a constant to your function, you're increasing it by that many units. When you subtract it, you're decreasing it by that many units. So it's a vertical shift up and down. And now when you graph this, you're going to see a whole bunch of functions that look the same. They're just vertically shifted up or down depending on our value of c. So this one was that shift up by 6 units, and here was that shift down. I can't remember what c value I used. It must have been -2. Yeah, -2. And then there was like a +1. But you can kind of get an idea now about what these solutions actually represent. So when you say +c, you're saying that any of these graphs could represent this derivative. What you're going to do now is you're going to let x equal 1, and you're going to let y equal 3, and you're going to solve for c to find a particular solution. So instead of having this infinite number of families of solutions, we're going to find the actual solution that corresponds to this point. Now, it doesn't look like we found it yet, because if x equals 1, I don't see that y equals 3. And I mean, you can go ahead and look at your table at all these different functions. If x equals 1, I don't have a 3 yet. But we'll solve for it and find it. This should not be like a guess and check situation. So you're going to let y be 3, and you're going to let x be 1. and you're going to solve for c. And you're going to get 3 equals negative 1 plus c. Add 1 to both sides, and you'll get c equals 4. So your particular solution is y equals negative 1 over x squared plus 4. And then if you were to graph that, negative 1 over x squared plus 4, you would get the graph that corresponds to our solution. I don't know if you can see the colors on here. It looks green to me, but you would get this function, and this does indeed have a point. Gotta scroll over to get it, I think, at 1, 3. So that's the particular solution that corresponds to this information that you were given. We're going to do like 2 more of those, but are there any questions here? So for B, and I want to make sure I'm showing you the different ways you're going to see this on WebAssign. We'll just use the Newton notation. F prime of x equals the cosine of x. And then we'll say that f of pi over 2 is equal to 5. And that should cover it as far as the notation you're going to see for first derivatives. So to get f, you're going to take the antiderivative of your derivative. F of x is going to be equal to the integral of the cosine of x dx. If you want one more step, I'll put one more in here. I think I put this in the earlier notation, but the integral of the derivative is just whatever your original function is. So take your f prime, take the integral on both sides. It's kind of like an inverse operation here where the integral like undoes the derivative, and then you just get regular old f of x on the left-hand side. And then you'll integrate, and you'll ask yourself, what function has a derivative of cosine of x? Well, I know that the derivative of sine x is cosine x. That must mean that f of x is sine x plus c. And I always double check these, always, always, always. The derivative of sine x is cosine x. Excellent. And then the last thing you need to do here is just evaluate the function to get 5. So I'm going to say that f of pi over 2 equals 5. So I have the sine of pi over 2 plus c equals 5. And then you have to know your actual trig function values. The sine of pi over 2 is 1. Subtract 1 from both sides and you get c equals 4. And don't forget to rewrite your function when you're done. F of x equals sine x plus 4. So going back to your last line here, and then once you find the value of c, actually substituting it into your function. Let's do one with a second derivative. Example 5. Find S of t. Oh, wait, you know what? Before I do that, I want to remind you of your rectilinear motion formulas. Recall. Sorry, I'm getting carried away with my differential equations here. A is your acceleration. That is the derivative of the velocity with respect to time, which was also known as the force of gravity. Negative gravity, because gravity heads downward. So G is positive, but it gets the negative applied because it goes down. But A represents acceleration. And this, by the way, was from 2.4. V of t is negative G of t plus V sub naught. This was your velocity. And S of t was equal to negative 1/2 G of t quantity squared plus V sub naught t plus S sub naught. Now, you can kind of see here, heading this direction, how you got these quantities using integration versus working in the opposite direction and taking derivatives. So if I can remind you, the acceleration was the derivative of the velocity and the second derivative of the position. And then, of course, what else was I going to say here? The velocity is the derivative of the position. I mean, that kind of goes without saying. Anything else I want to say about this? I don't think so. But we're just going to work a little bit with these formulas and differential equations. Nothing too crazy. It's just important to know which one's which. So the original function is, if you're heading top to bottom, the original is your position. You take its derivative and you get velocity, and you take its derivative and you get to acceleration, kind of working your way down. Now I'll give you example 5. Oh, you know what? It might be helpful to see these in terms of integration. So if the velocity is the derivative of the position, then you can integrate the velocity to get to the position. So the integral of V of t is S of t. Oh, dt, I forgot my dt's, you guys. Yowza. If you wanted to think about it that way. And then the integral of the acceleration gets you to the velocity. Actually, I don't need dt here. I didn't actually integrate. I just freaked out and put it there. So you can work those back in the other direction. Okay, I think that was all I had to say about that. All right, example 5. Find S of t, the position function, for A of t equals e to the t meters per second squared. And we're going to use the initial information that S of 0 is 0 meters and V of 0 is 4 meters per second. So I gave you an acceleration function. To get to the velocity function, you're going to integrate that. So remember, acceleration is like the third one you hit when you're taking derivatives. So you're going to go up by integrating to get to velocity. And then we're going to go up again to get to the position function. So we're going to start by going from acceleration to velocity, and then we're going to head back up to position. So v of t is going to be the integral of a of t dt. That means that v of t is going to be the integral of e to the t dt. And that means v of t is e to the t plus c, because the integral of e to the t is e to the t plus c. All right, once you have your velocity function, you're going to go back to your initial conditions and evaluate v of 0 and set that equal to 4. So v of 0 is e to the 0 plus c, and we're setting that equal to 4. So this is the equation that you're solving. And remember, this came right there from that initial condition. E to the 0 is 1. Subtract 1 on both sides and you get c equals 3. But we're actually looking at two different derivatives here, which means we need to apply this process twice. But now we can at least say that v of t is e to the t plus 3. What you were asked to find was s of t. In order to get s of t, we're going to integrate v of t dt. And s of t gets us all the way back to the top. So s of t is the integral of e to the t plus 3 dt. And so we're going to integrate here, and then we're going to use the initial position s of 0 equals 0 to solve for our next value of c, and then we'll get the position function. So s of t is e to the t plus 3t. Anytime we're integrating a constant, we just slap that variable onto it, plus c. Questions so far? I feel like I'm going through this a little quickly. I want to make sure that we're good to go here.
How did you get the t on 3? Like you did 3t?
So anytime we're integrating a constant, think back to the derivative. So the derivative of 3t is 3.
Oh, okay.
Sometimes it helps to see it that way instead. But anytime you're integrating a constant, you just tag that variable onto it.
Okay, I get it. Thank you.
You're welcome. Any other questions here? Okay. Wonderful. We're going to look now at s of 0. And remember, I gave you this initial condition that s of 0 is equal to 0. So I have e to the 0 plus 3 times 0 plus c equals 0. Don't forget you're solving for c, so don't evaluate c at any number. And then e to the 0 is 1. 3 times 0 is 0. Subtract 1 on both sides and you get c equals -1. And now you can write your position function s of t as e to the t plus 3t. Don't say plus -1, just say -1. Oh, and you know what? Your book might your book. WebAssign might want units on this. You know what? They'll probably give you a unit though, so I wouldn't worry too much about it. But technically, S of t was in meters, so it's this many meters, and your velocity was in meters per second, so it's technically meters per second. But you know, they give you units, so I'm not too worried about that. Okay. All right, that's all I had to say on 4.8. I do want to cover the FTC part 1 because it's very short and I have like 18 minutes, and that's probably the perfect amount of time to do FTC part 1. And then we can focus more on FTC part 2 next time, which is really the bread and butter of everything we're going to be doing. Okay, any questions on 4.8 before I move forward? Excellent. So I'm going to do a really quick synopsis of what we're skipping in chapter 5. I don't like to skip the theory, but my goodness, it's very, very heavy here at the early part of chapter 5, and you're never going to use it again. That's why I just can't justify spending 2 days worth of class time on it. Okay, let me show you my book here. It has some pretty decent pictures. Give you a little tour of these area functions. I'm going to have to adjust my camera. Hold on a second. Okay. Okay, so what I'm showing you right now is a page from 5.1, which is called area. And basically what you're doing in 5.1, which we're not going to do, is you're summing up all of these areas. And the end goal, if I can, it's not there, it's up here. I'm upside down now. Here we go. Okay, I'm looking at this upside down, so I'm going to have to reorient myself. The idea here is that at some point in 5.2, you learn how to actually integrate a function, which is to find the area under a curve. That's really the point of integration. So if you think about taking a derivative as being more about finding slopes of tangent lines and finding places where you have horizontal tangent lines, mins and maxes, stuff like that, that's more what we use the derivative for. And there are other applications of the derivative. One that I didn't go through was called Newton's rule for approximating zeros. I sometimes cover that. I find that you don't really use it hardly ever. So I don't know. I didn't cover it this semester just because I didn't really feel like we had time to put emphasis on it. But either way, a big major application of integration is finding the area under a curve. So the idea here is that you have this function f of x, and if you want to find the area under the curve of the function, it's not the same as finding the area of, for instance, a rectangle or a trapezoid. So for those, we have geometric formulas. But the idea here is that you set up a series of rectangles underneath this curve. When you do that, you can start to get an approximate value for the area under the curve by just adding up the areas of each of these rectangles. But clearly it's not perfect because you have places here where under the curve, maybe you're missing this area on the rectangle right here, and maybe you included too much right there, but you kind of get close and you get a good approximation. Well, what happens with integration is you start to make an infinite number of rectangles that are so skinny that you don't have these pieces anymore where you have this missing space or you have this space that you're covering that shouldn't be there. You start to make so many rectangles that they start to sort of just get so close to each other that they become a much better approximation to the curve. I mean, notice if we even took these rectangles and split them in half, already you'd be getting a closer approximation because then you could cut that one off here, you'd get closer. You could cut this one off. Well, I guess that one wouldn't change very much, but you could cut that one off here and you'd get closer. And the more rectangles you fit in here, the more more times you partition this space, the closer you're going to be able to get to the actual area under the curve. But you're asking like, whoa, holy cow, doesn't that seem like a lot of work? It is a lot of work. But what you're going to find here with integration is that the actual area under the curve is the integral from A to B. So as long as we know how to take the integral and find the antiderivative, what we can do is we can use the fundamental theorem of calculus, which you're going to learn in 5.3, and you're going to evaluate that integral from A to B, and you'll be able to get an exact value for the area under the curve. So 5.1 basically just kind of takes you through all these approximations, and you set up all these little triangles. I'm trying to get this one in here. That look like this, and you partition it a certain number of times, and you keep trying to get closer and closer and closer so you can get approximates. That's what you do in 5.1. And then in 5.2, you actually are starting to take all these summations. Let's see if I can get this page in here. Oh. This way. Sorry, I'm totally upside down. That are of this form. So you start taking the function and evaluating at all these little sub-intervals. And it's quite a lot of work, as you can imagine, using all these sums. So it's a lot of formulas. It's a lot of crazy sums. If you're really interested in it, feel free to leaf through it. I highly would recommend that you do that. But you can kind of get a sense here at what's happening just by even looking at these values that you're coming up with as you approximate these sums. It's interesting. You learn how to take those limits and then you apply that, but it's not something I want to spend a lot of time on. I wanted you to see it because I want you to kind of get a sense for what it means to integrate. But as far as we're concerned, if I ask you to find the area under the curve, I want you to do it using integration without getting these approximate areas. You will work a little tiny bit with approximations in Calc 2 when you approximate integrals, but it's not really the same process. You'll be using formulas, but they're much simpler. So not as big of a deal there. And you won't need that stuff, just the general gist of it. Okay, so I'm going to do FTC part 1. It's pretty quick. There's not a ton that we're going to be doing with part 1. Most of what you're going to be doing with the FTC deals with part 2. There are some semesters where I don't even cover part 1, but every once in a while you'll come across a definition or a theorem that uses it in the theorem or definition. So I don't want you to be like, wait, what is this? So I'm going to introduce it to you, but it's not something I'm putting a lot of emphasis on. I just want you to see it. I find it funny that they call it the Fundamental Theorem of Calculus Part 1 because it's not something you use very often. It's, I guess, an important result that is applicable to many ideas in calculus. Part 2, like I said, is what we're going to be spending most of our time looking at. If I call it FTC, that's what I mean. Okay, so part 1 of the theorem, and I'm going to give you a picture that goes along with this. We're going to let f be continuous on the closed interval from A to B. The function I, defined by I of x, and I know this is weird for you because you're used to thinking of I as being this interval, but you'll kind of see how it relates, equals the integral, and here's where you're starting to see this definite integral come into play. So this is an integral with upper and lower limits of integration. The lower limit of integration is a, the upper limit is x. We're going to be applying this a lot in the FTC part 2, but I'm going to show you a picture of what this integral represents in just a minute. A is a real number, x is a variable. Has properties that is continuous on the closed interval. and differentiable on the open interval. Moreover, I prime of x is equal to the derivative with respect to x of the integral of a to the x f of t dt, and that is equal to this function f of x for all x in the open interval. And if you're kind of confused, that's not a weird reaction. So to get sort of a sense of what's happening here, imagine that you have this curve y equals f of t, and we'll let the x-axis represent t in this case. You're going to look at that on the interval from a, instead of a to b, you're looking at it on this interval from a to x. And remember, x is just going to be some value inside your closed interval from a to b. And I of x represents the area inside here underneath your curve. So when we write a definite integral, it's going to look like this. We're going to see a bunch more of them tomorrow, and I'm going to give you a real definition for that. You're essentially just saying that this upper endpoint x can be moved. It can be any value somewhere inside the closed interval from a to b. And depending on where I move this value of x, the function for your area is going to change, and it's going to depend on where x is located. So if we move this x around, I mean, if I moved it to the left, imagine if you moved it over here, the area under the curve would be lower. So it's very dependent on that. So the area of underneath your curve is a function of x being this endpoint of where you move it. And that's all this is really saying. So if I is the area, well, I prime is just the derivative of this area, which gets you back to your function f of x. So all I'm going to do here is I'm just going to ask you to calculate the derivative just so you've seen it, you've used it, and we're not going to, like I said, we're not going to spend a ton of time on it. I want you to see it here and use it here, and then next time we'll pick up and talk about some properties. But this is the picture that goes along with this. Everything we do after this will be concrete. But I'm just going to give you example 1, which is calculate the derivative. And that's all I'm going to expect you to do here. The first one is going to be the derivative with respect to x of the integral from 1 to x of the sine of t squared dt. Now notice that your variables here inside your function and your variable of integration are going to match. But the variable that's inside your limit of integration is going to match the variable with which you're taking the derivative. Now, as long as, and I wrote this in the definition, a is a real number and x is a variable, you can apply this directly and just say that your derivative is just equal to f of x. A is a real number, x is a variable. All you have to do here is just apply this directly and say that your derivative is the sine of x squared, not t squared. Remember, our function was f of t dt, but we were taking the derivative with respect to x, and we found f of x. By the way, when we actually go through part 2, which I think it's helpful to do part 2 first, some books called this part 2. I feel like that's better because I feel like it's easier to teach this if you've seen part 2 first. I used to teach it in reverse too. Maybe I should start doing that again. But I think once you go through part 2, we can revisit this and you can get a better sense of why this is true. But right now we're just finding the derivative, which means we're just using this formula. That's it. You can switch those variables around, by the way. As long as they match where they're supposed to match, that's all that matters. If we're taking the derivative with respect to t, then our derivative is going to have some function of t in it. So notice how f of x and dx match. We're going to have the same thing happen here. Here your x's match, and then your outside variables are t. Your lower limit's a real number. Your upper limit is a function. That's a variable. So when you take this derivative, you're going to get 3 divided by, instead of the square root of x, the square root of t. So you're taking the derivative with respect to t. You're just going to end up getting 3 over the square root of t. That's it. I'm going to show you an example, however, where your variable is not just by itself, where it's some function of t. And we'll do that. So this one is d dx, the derivative with respect to x. And this one will be 1, the integral from 1 to x cubed of the tangent of t dt. Now the only difference in this case, and you have to check for this, your lower limit's a real number, but your upper limit is some function of x. If that's the case, no big deal. You're going to sub it out. We're going to let u be that function of x, and then take its derivative. Du dx is 3x squared. And then when we take d dx, we'll just chain on that derivative of your inside function. So now when you take your derivative, you're going to take your tangent. We're taking the derivative with respect to x. So we're going to take the tangent of, and our variable here is x cubed. And then we're going to chain on the derivative of the inside function, which is 3x squared. And if you want to rewrite that as 3x squared tangent x cubed, be my guest. And that is all I'm going to have you do for FTC Part 1. We will pick up tomorrow with FTC Part 2, and then we'll start substitution after that. Because technically, even though Part 2 is very, actually we'll do some properties of definite integrals first, which is actually pretty quick. My goal though tomorrow is to start doing some substitution tomorrow, so you're not seeing it for the first time asynchronously. Go ahead, Burfin.
Why did you put dt instead of dx there?
Here?
Yeah.
So these two variables always have to match, because remember when you're taking an integral.
Well, the t's have to match.
Yeah, so whatever these two variables are, they have to match, because this is your variable of integration. And then when you apply this, and this is why I think it's better to see this in reverse, so we might revisit this after we learn Part 2. These two have to match, because now your new variable is going to be x, and that's going to have to match the variable with which you took the derivative. So this variable has to match what's in your answer. So each time when you take the derivative with respect to whatever variable, that's the variable that gets entered into your answer.
Okay.
Oh, good question, Renee. Yeah, we don't have to include a plus c, because technically we're taking a derivative here and we're using it straight from the theorem, and the theorem does not include it. When you take a derivative, you don't worry about it. So yeah, there's no plus c that's involved here. Okay. All right, it is 8:11. I am going to put up some homework for you guys, mostly for antiderivatives, and then just a couple of these derivative FTC Part 1 questions. There aren't very many of them. And then tomorrow we'll pick up with FTC Part 2. We'll work with some properties of definite integrals in 5.4, which is a little bit shorter, but the properties are really important to cover. And then hopefully tomorrow we can get started on a little bit of substitution, and then your asynchronous work over the weekend will start 5.5 and we'll finish 5.5 Monday. 5.5 is like a 2-day event. The event of the semester. Oh, it's so good. Okay. Have a wonderful evening, and I'll see you tomorrow.
You too. Thank you.
Thank you.